This is video 63 in our series on tensor calculus. In this video, we're going to take a closer look at the properties of the normal. And we'll also find an explicit formula for evaluating its vector components. In video 58, we introduced the normal as having these two properties. Well, today we want to dig into these a little deeper. So the first thing we'll do is recognize this. This first equation up here is an equation with one free index. So let's raise this index. Of course, we do that by contracting it with the contravariant metric tensor. So it's going to look like this. Of course, the left side is still going to be 0, but on the right side we'll have n hat dotted with s alpha, and that's going to be contracted with s alpha beta. All right, well, that raises the index, so this is going to be n hat dotted with s beta in the upper position. And of course, we can rename beta to alpha, and we get n hat dotted with s alpha. Okay, so this expression 0 is also equal to this expression, so we can write that up here. So this is another fact that is true, another property of the normal. And it says something that may already be obvious to you, but maybe not. And that is that if the normal is orthogonal to or perpendicular to the covariant basis, then it's also perpendicular to the contravariant basis. And that makes sense because if S alpha in the lower position, if the covariant basis lies on the tangent plane, then the contravariant basis also lies on the tangent plane. So if these are perpendicular, then these will be also. But the implications go a little bit deeper, so let's look at it this way. We said along the way that S1 in the lower position and S2 in the lower position combined with the normal is a way of forming a basis for our tangent space. And then later on we derived the contravariant basis vectors, S1 and S2 in the upper position, and we said that this could be an alternate basis as well, and it would also use the normal. So the point is this, that our tangent space can be represented by either of these as bases. And although these two right here are not the same, of course, as these, the normal is. There's only one normal. So what that means is that the normal is not considered to be either contravariant or covariant. And you'll notice there's no index here. So when we transform back and forth between contravariant and covariant bases, the normal is unaffected. It is not part of the transformation. All right, now let's look at this. Let's take the expression here and express each of these vectors as a linear combination. So we'll take n hat dotted with s alpha, and we'll form a linear combination by using the covariant component and a contravariant basis vector in the ambient space. So this is equivalent to n hat. Now we'll dot that with a linear combination forming s alpha, but this time we'll use the shift tensor. So we'd use zj alpha with the covariant basis vector zj. You can probably already see where this is headed. The dot product of zi and zj is just delta ij. So this is going to become ni zj alpha times delta ij, and of course that absorbs the j index, leaving us with ni zi alpha. So this is yet another equivalent form of our property here. So this is the same as this, and that means we can include this relationship as well. This is equivalent to the first property over here, the contraction of the covariant vector component of the normal with the shift tensor is equal to 0, and that's the equivalent of the fact that the normal is orthogonal to the covariant basis vector. Well, I think you can see without going through the whole thing again, if we started with n hat dotted with S alpha in the upper position, followed through with a similar derivation like this, we'd also achieve this result. We'd find that it's equal to Ni in the upper position times the inverse of our shift tensor Z alpha I. So this one is equivalent to this second term right here. So any one of these four expressions gives you the idea that the normal is orthogonal to the basis vectors. All right, now concerning the second equation down here, this one's easy. We know what it means to take a dot product. That's just the contraction of a covariant vector component with a contravariant vector component. So this would be the equivalent to the dot product here. And of course the order doesn't matter, so just for completeness we'll write it this way as well. So these two expressions, all three of these expressions are the equivalent. They're all going to be equal to 1. All right, that having been said, let's now move on and see if we can derive an explicit expression for the vector component of the normal. To do that, we're going to find the cross product between our covariant basis vectors S1 and S2. Now you'll remember from video 52 that the cross product is a vector operation that produces a third vector that is orthogonal to each of the two inputs. Well, if S1 and S2 lie in the tangent plane and W is perpendicular to both of them, then it's going to lie in the direction of the normal. Okay, well, how do we go about this? Well, we first appeal to an expression we derived in video number 60. And if you look at this closely, you'll see that it's nothing but a linear combination. We've got a vector S alpha that's equal to a contraction between vector components and the ambient basis vectors. Well, that means that our shift tensor is just the set of vector components for S alpha. And with that, we can then express the cross product in tensor calculus syntax. We'd say that Wi is equal to epsilon ijk times the vector component for S1 here, and that's just going to be zj1 times the vector components for S2, and that's going to be zk2. And it's as simple as that. That is the cross product between vectors S1 and S2. But of course we don't like the hard-coded index references right here. And we'll deal with that the same way we dealt with things back in video 44 when we were defining the expression for determinants. First of all, we note that indexes 1 and 2 are anti-symmetric. Now you know that already from video 52 that if we switch the order of these two factors, we'll change the sign of the output. But you can see it also from our old technique of first of all renaming J and K here, then swap the order of J and K, which changes the sign, and then swap the order of these two factors, which does not change the sign, and we're back where we started, except 1 and 2 have been swapped here. In other words, 1 and 2 are anti-symmetric. In fact, what we can say is that these lower indexes are skew-symmetric. Okay, well we can capture that relationship as we did back in video number 44 using the permutation symbol. Remember how this works when alpha is 1 and beta is 2, and of course we just have this expression up here, and this is a positive term. But if alpha is 2 and beta is 1, then this is a negative term out here, so swapping the order will change the sign as we expect. Okay, well now we want to isolate Wi on the left side, and we do that by forming a contraction of E alpha beta in the upper position. We have to do that on both sides, of course. So on the left-hand side, E alpha beta contracted with E alpha beta is just the same as delta alpha beta alpha beta. And you remember the identity that when we have a contraction, that's equal to 1 times delta alpha alpha, and delta alpha alpha is equal to 2, so this is equal to 1 times 2, or 2 factorial. So this contraction is 2 factorial, and if we then divide both sides by 2 factorial, we will have isolated Wi. All right, well, there's one other thing I want to do. We really don't like the fact that we have this permutation symbol in our expression. It's not an absolute tensor, it's a relative tensor. So life is a whole lot easier if everything in the expression is an absolute tensor. So let's do this. Remember that epsilon alpha beta is defined as 1 over the square root of s times e alpha beta. And that in turn means that e alpha beta is equal to the square root of s times epsilon alpha beta. So let's make this substitution, and then everything in this expression will be an absolute tensor. So the product of the square root of s here with epsilon alpha beta combined together is the same as e alpha beta up here. Okay, so this is our final form for the cross product of S1 and S2. And of course, being a cross product, we know that vector W is orthogonal to both S1 and S2 and therefore points in the direction of the normal. However, it's not a unit vector, and that's what we need. So what we have to do next is to normalize vector W by dividing it by its own magnitude. And to do that, of course, we have to know what the magnitude of vector W is. So let's go over and calculate the magnitude of vector W, and then we'll return here to finish up. To find the magnitude of vector W, we just need to find the dot product of W with itself. And of course, in tensor calculus terms, that means just evaluating this contraction. All right, well, Wi in the lower position is what we just derived a couple of minutes ago right here. And to find this factor, we just raise the I index and flip the position of each of the dummy indexes. Now, notice that J, K, and alpha and beta are all dummy indexes, and they're already in use over here, so I've got to pick different letters for those dummy indexes on this side over here. Okay, well, let's clean this up a little bit. This contraction is really the magnitude of vector W squared, so we'll just represent that as W squared. And next we'll collect all the constants. We've got the square root of s twice and 2 factorial twice, so we'll make that s divided by 4. And then epsilon ijk combined with epsilon irs is delta irs ijk. And then epsilon alpha beta with epsilon lambda omega is delta alpha beta lambda omega. And then we've got all of the shift tensor terms. Z, J alpha, Z, K beta, Z, lambda R, and Z, omega S. Next, we'll pick on this first delta term, delta IRS IJK. Of course, there's a contraction here, and if you remember the identity, that means it's just equal to delta RS JK. And by definition, that is delta RJ delta SK minus delta RK delta SJ. So we will substitute this expression up here with this result. All I did was to replace this term with this one, and of course I rearranged the terms a little bit. Okay, well next we want to distribute this factor here into each of these terms inside the parentheses here. Now, as we multiply this times this term, notice that there's some indexes that get absorbed. The R index here is absorbed, leaving us with J here. The S index is absorbed, leaving us with K right there. As we multiply this expression by the second term here, the R index is absorbed, leaving us with K, and the S index is absorbed, leaving us with J. Okay, well, next we will expand out the meaning of delta alpha beta lambda omega. So we've got W squared equals S over 4, and this expression by definition is delta alpha lambda delta beta omega minus delta alpha omega and delta beta lambda. Okay, now in this second expression over here, notice there's some contractions here. Zj alpha contracts with Z lambda j to form a delta lambda alpha, and Zk beta contracts with Z omega k to give us delta omega beta. And then over here, Zj alpha contracts with Z omega j to give us delta omega alpha, and then Zk beta contracts with Z lambda k to give us delta lambda beta. Okay, well, don't miss this. This term and this one together form this delta factor. These two together give us this one. These two together give us this one. And these two together give us this one. Next, we'll expand all these terms out. We're going to have to multiply this term by this one, and then by this one, and this term by this, and this term by this. Okay, so as we multiply this first expression here by this one, notice the alpha index is absorbed here, and the beta index is absorbed right here. So that's going to give us W squared equals S over 4 times delta lambda lambda delta omega omega. Okay, as we multiply this term by this one, we see that the alpha index is absorbed here and the beta index is absorbed here. So that's going to give us a minus delta omega lambda and delta lambda omega. All right, when we multiply these two terms together, the alpha index is absorbed here, the beta index is absorbed there, and that gives us a minus delta lambda omega delta omega lambda. And finally, as we multiply this term by this one, it'll be a positive term, and alpha is absorbed here, beta is absorbed there. That gives us a positive delta omega omega and delta lambda lambda. All right, well, now we have W squared equals S over 4, and in the parentheses, delta lambda lambda is just 2, and so is delta omega omega, so 2 times 2 is 4. The second term, the lambda index is absorbed, leaving us with delta omega omega. Well, that's just equal to 2. And same thing here. Omega is absorbed, leaving us with delta lambda lambda. Well, that's just 2. And the last term, delta omega omega is 2. Delta lambda lambda is 2. 2 times 2 is 4. All right. You expand all this out. 4 minus 2 plus 4 is 4. 4 cancels this 4 out, so the whole thing evaluates to S. And that means, of course, that the magnitude of vector W is just equal to the square root of S. And with that, we can return back to our original line of investigation and complete the derivation for the normal. Okay, well, now that we know what the magnitude of vector W is, the expression for the normal is just this expression divided by the square root of S. So what we have here is an expression for a vector that is orthogonal to both S1 and S2 and has a length of 1. And that, of course, matches our definition for the normal. All right, there are a couple of things I want to do before we finish up. Let's form a contraction using zi omega here. And of course, we have to do it to both sides. Zi omega. Well, it's easy to demonstrate that these lower indexes, alpha, beta, and omega, are skew symmetric. We can play the old game of renaming any two indexes, like I and k, for example, and we'd rename I and k here, swap the order of these factors, and swap I and k back, which changes the sign, which shows us that switching beta and omega will change the sign of the expression. So that's something that's true for any one of these indexes. They are skew symmetric. Well, alpha, beta, and omega are surface indexes, meaning they can only have a value of 1 and 2. So it's impossible to assign values to alpha, beta, and omega without establishing a duplicate. For example, if alpha is 1, beta is 2, then omega can only be 1 or 2, so it's going to duplicate one of these other two. In other words, it's always going to be equal to 0. It's never possible to establish unique values for alpha, beta, and omega because they're skew symmetric, and we can't have unique values for all three at the same time. Well, remember this expression on the left is just an alternate expression for the dot product of our normal with basis vector S omega here. Now that goes back to the early part of the video where we said that these two expressions are the same. So that's just another way of demonstrating that this expression we've come up with is in fact orthogonal to all of the basis vectors. The other thing is we want to find the expression for the normal component with an upper index, the contravariant vector component for the normal. Well, that's easy. We can always just raise the I index and flip-flop the position of each of the dummy indexes. This is something you can always do with any tensor equation. Okay, well, as an exercise, you might want to see if you can take these two definitions and show that this contraction is equal to 1. This, of course, is the dot product of the normal with itself, and being a unit vector, this is something that you should be able to demonstrate. All you have to do is to go through the same steps we did in finding the magnitude of vector W. All right, with all of that, let's wind the video down with a brief recap. The first thing we did was to expand on our understanding of the basic properties of the normal. We saw that not only is the normal orthogonal to the covariant basis vectors, but it's also orthogonal to the contravariant basis vectors as well. All of these basis vectors lie in the tangent plane, so all of them are perpendicular to the normal. And that in turn tells us that the normal is the same normal in both cases. We said that the normal is not contravariant nor is it covariant. It's simply a vector, and it applies in both cases whether we're using the covariant basis or the contravariant basis. All right, we then went on to use the shift tensor to derive this expression as an equivalent form of this. So using the vector component and the shift tensor will give us an expression that's equivalent to this, so we can use this in place of this one anytime it's appropriate. Likewise, this expression is the equivalent of this one and can be used in place of it whenever we need to. And we also noted that the fact that the normal is a unit vector means that the dot product of the normal with itself is 1, and that can be expressed in this form using vector components. All right, and then we spent the rest of the video deriving these expressions for the normal. We have an explicit expression for the covariant component of the normal using this expression, and this one gives us the contravariant component of the normal. We showed very briefly that this has the same properties that we described up here. If we contracted this with zi omega, for example, we get 0, which proves this property, and then if we contract these two together, we'll get 1, and that would prove this property. All right, in the next video, we're going to use this expression to evaluate the normal for each of our sample surfaces.